Swayam Prabha. Digital India. Educated India.
Hello everyone. You have already introduced with some algebraic structures which are known as rings and fields in particular, where you have seen that the set of objects can relate with each other by two different binary operations. And you have seen many such properties and applications of those ring and field data structure. Today we will be starting our discussion for a new algebraic structure called groups. So groups basically are defined over only one binary operation. So we say that let G is set of elements and O, let this be the binary operation. Then with that we define G with the binary operation O as a group if these properties are satisfied. Number one, we have closure property. So the closure property says that it's just extended from the binary operation closure, that for all A, B belongs to G, I will also have AB operated together will also belongs to G. The second property that we talk about is the property of associativity. So the property of associativity says that for every element A, B and C that belongs to G, I can operate BC first and put the result operated with A. That will exactly produce the same answer if I operate AB first and try to operate the result of that with C. So in general, generally you can write that if you say A0 operated with, or rather A1 operated with A2 operated with up to AR, which is operated with AR plus 1 up to AN, then you can also write it as, so you can also write it as the same as A1, A2 up to AR, AR plus 1 up to AN. So here I just have assumed that my N belongs to Z plus and N greater than equal to 3. So these are my assumptions. So this is the general rule of associativity, which says that you can put the brackets and do the operations in any order. The third principle of having something as a group is the existence of identity element. So what is an identity element? Identity element says that for all elements A in G, there must exist an element E such that I have A operated with E will give me the same answer as E operated with A, which is basically my A itself. The fourth property that we need is the existence of what we call as inverse element. So the inverse element says that for all A belongs to G, there must exist an element, let's say, which is X belongs to G. This element may not be unique, whereas this element we will try to prove all these things. So for each A, I can get a corresponding X such that I can write that AO X equal to XOA, which is E. So if this 4 property gets satisfied, then only I can call it that my G is a group. Additionally, along with these properties, we have something called commutativity or abelian group or commutative group. We call it a group is commutative for all A, B belongs to G if I can write the operation in any particular order. So this is an additional property of the groups when we call this group as commutative group. And by the way, the name abelian comes from the scientist known as Henry Abel. So it's Niels Henry Abel, the scientist, that keeps the group name. So let us now have some examples of such kind of a group. So let us try to have some examples. You can easily understand the group comprising of the set of integers with plus is basically a group, because here, so this is a group, and also if you think of the set of rational numbers with plus forms a group, the set of real numbers with addition forms a group, the set of complex numbers with addition forms a group. So all of them, all these 4 are examples of, in fact, abelian groups. Because addition, you can do it in any order. Here my identity element is 0, and my inverse element, since it's an additive group, for each element A, I call minus A as my inverse. Now if you tweak this operation slightly a little bit, then you see that this Z with multiplication, R with multiplication, Q with multiplication, C, that is the set of complex with multiplications, all these are not groups. Why? Because clearly here 1 by A, so first of all let me figure out that if this has to be a group, then I have to make my identity equal to 1. So inverse should be 1 by A. So this does not exist. Here in these 3 cases, though 1 by A exists for every element, but here also identity is 1, but inverse for 0 does not exist, which is 1 by 0 does not exist. So therefore all of them, this set is all of these are not groups. Whereas if we change a little bit in these sets to make them, let's say we have non-zero elements of Q, non-zero elements of R, and non-zero elements of complex C with multiplication, then this forms a group. So these all are, again, if you try to see this set is again a group. So this is perfect. So all these are abelian groups. So now more interesting examples you can find for the groups is, so this is one kind of an example that we did. The more interesting example of groups you can find here, where your R plus star is a ring, then your R plus is a group. If you see your F plus star is a field, then your non-zero element of F, that is the non-zero element in this field set with the multiplication operation, forms a group. And if you look closely, all of them are abelian or commutative group as well. Now, the third kind of example that we always find is when we go for this kind of groups. Like, for example, if Zn with respect to plus, so that is the set of all equivalence classes of n for the integer modulo n. So this is definitely an abelian group. And more so, if you dig, just for curiosity, I just give you a part of an exercise that you will also find that the set of elements, let's say this set prime with non-zero. So this set of equivalence classes, when you divide by prime, if you take the non-zero set of primes with respect to multiplication, this also forms abelian group. And our final example, our final fourth example, is as follows. So we may think that since this is a ring, so we will consider the units of the ring. So if we consider the units of this ring under the multiplication operation. So what are the, for example, for Z9, what are the units for Z9? So the units for Z9 is basically would be 1, 2, 4, 5, 7, 8. Why? Because this will form by the elements of the form A such that the GCD of A and 9 is equal to 1. This is the unit, because for those elements A inverse exists as per the definition of units. So now you see here, you will easily find that this is an example of a ring under multiplication. So U9, and this is a ring. So U9 with star, this will form a group. In fact, an abelian group. So here you can find that the identity element here, the identity element, if you try to see, it is 1. The inverse, if you try to find some of the inverses, I am writing 2 has the inverse as 5. Check it. 4 has the inverse of 7. 8 has the inverse itself. 8 has the inverse itself. Please check it. So we will see that, so this is particularly forming so this forms a group, an abelian group. In fact, you can write it as an abelian group and also check for the abelian condition. So this forms an abelian group. So these are some of the examples that we can do. So set of integers reals with plus, non-zero reals, rationals complex with star. Then if it is a ring, R plus, if it is a field, the non-zero element of the field with star. So modulo n operations all possible equivalence classes with plus, all possible equivalence classes of prime p non-zero with star. These are all. And if you are more curious that what kind of units would form a ring, so in general I could give you the formula where the units of Zn plus star, so the units of Zn plus star will form a ring where n is equal to 1, 2, 4, a prime to the power exponent or 2 prime to the power exponent. So all this category will give you a choice of ring. All this category. Choice, the units of these rings where n equal to 1, 2, 4 p to the power a and 2 p to the power e will be a form a group. You please verify and try to think over that why I gave these two conditions, why the others are not a ring. So Z16, the units of Z16 will not form any group, whereas the units of Z17 and the units of Z18, which is 2 into 3 square, so 2p to the power e, this will form a group. Please try to understand by having some examples of this. So now, since we have declared groups, so something we will define which is known as order of groups. This is nothing but the number of elements that are present in the group. So a group G, we write it in this way, is the number of elements in G. So as you can see that this could be either finite, the order could be infinite. Some examples of such infinite groups, we can find that this is an infinite group of infinite order. Some examples of finite is that this is a group which is finite because the order of this group is n. Similarly, we have declared the group Zp star in the earlier side with star, which has order p minus 1. So what would be the order of the group that we defined as the units of Zn? So for the units of ring Zn plus star under star, so the group order for the units of n under star is equal to phi n, where we have studied that it is Euler phi function. Okay, so this is the number of co-prime numbers with respect to n, that is which the number whose GCD with respect to n is 1. So we have seen what is the formula for n. So if you remember, it is just n into 1 minus 1 by p1, 1 by p2. If you can represent n as p1 to the power e1, p2 to the power e1, p1, p2 are all primes. So we can write it in this way. So these are all examples of finite groups. With that, so let us now try to understand some of the basic properties of groups. So here we come with the properties. So our first fundamental property is identity element is unique. How do you prove it? So let us assume, to prove it, let us assume I have two elements E1 and E2 belongs to G as my identity. Now, if this be the case, then what will happen that since assuming my U1 to be the identity, if I operate it with any other element, I get back that element. So, this is assuming U1 as the identity. And assuming E2 to be the identity, if I operate with any other element present in the group, I get back that element. So, this is what we get by assuming E2 to be the identity. So, what these two reveals? It reveals that these two should be same because U1 over E2 operations due to binary composition closure always result in a same thing. So, these two are the same. That's why we have proven it. The second propositions that we could write over here is that our inverse is unique. So, when we say our inverse is unique, we want to mean that suppose again we assume that for an element A, x1, x2 belongs to G are inverses of A belongs to G. So, I need to arrive at a contradiction or need to prove that x1 and x2 is equal. Since x1 and x2 inverses, so see x1, since it is an inverse of A, I can write x1 as this where E is my identity. I can write this as A O x2 because A O x2 will give me identity if my x2, assuming that x2 is also my inverse, A O x2 will give me the identity as per the inverse definition. Now I try to go with the associativity principle and do it this way. So, associativity will give me this. Now, assuming that again I know that x1 I have assumed it as my inverse of A. So, this will give me E O x2, which is basically the element x2. So, I have proven that this does imply that x1 is equal to x2, so the inverse is unique. So, let us move on and see some other properties of the group as well. So, these are the properties we call cancellation laws. So, the first cancellation law says that if for let's say G with binary operation O is a group, then for any three elements, if I take A, B, C belongs to G, and if I say AOB is equal to AOC, it implies B equal to C. This we call as left cancellation. Whereas, the opposite way we can think it as the right cancellation is as follows, that for every three elements we take and we have the property like A, O, or rather let us do it in this way, and we have the property like B operated with A is same as C operated over A, which imply B is equal to C. So, this is what we call as right cancellation. I leave the proof to you just to give you a hint of the proof. It's pretty simple. See, you are given with A operated over B is equal to A operated over C. And as per the group, A has a corresponding inverse element, right? So, let's say the inverse of A, since it is unique, so from now onwards, I will try to define A inverse as the inverse of A. Okay. For the multiplicative group, I will define this way. Of the additive group, I will define minus A. Now, I can operate A inverse with AOB and can operate A inverse with AOC. So this, due to associative rule, I can have this. So which means we basically form EOB equal to EOC, which gives me B equal to C. So the left cancellation law is proved. Similarly, the right cancellation law, the similar for the right cancelling. Okay, so just do it with yourself. So when we have this cancellation laws in our hand, so another interesting properties of another interesting notational property of group we can study is that what we call the division as multiplicative groups. So multiplicative groups, we say G under the multiplicative operation is a group, and then we write it in this way that A to the power 0 is E, A to the power 1 is A square is nothing but A operated over A 2 times, and so on. Therefore, A to the power n is basically A to the power n minus 1 into A, which is basically A into A to the power n minus 1. Both way we could write it. So this gives me the fact that, so all this points to this direction, that I have A to the power m operated over A to the power n is equal to A to the power m plus n, which is equal to A to the power n operated with A to the power m. This is for the multiplicative groups. So this is for the multiplicative operations. The counterpart we have as per our definition, as we said. So in this case, so just one point more to mention here. In this case, for the multiplicative group, I will assume my identity element to be 1. That is, since it's a multiplicative group, we denote it by this notation. And the inverse element of an A, I will denote it by A inverse. Because it's multiplicative, so that's why A and A inverse will give you A to the power 0, which is 1. So that's why it's a notational standardizations that I will try to highlight here. Now, for the additive groups, again here GO is a group. Now for additive group, I can see that I will write it in this way. 0A is my E, 1A is my A, 2A is basically A plus A. So just a clarification, this is additive, so I need to have addition. And we write it in this way. So therefore my NA is basically n minus 1A plus A, which is basically A plus n minus 1A. So this again points me to the fact that I can write MA plus NA is equal to M plus N into A, which is basically NA plus MA. So here again, I will try to figure out or rather notify my identity element. Since it's an additive, I will consider it as 0. And my inverse element of A, I will try to write it as minus A. Because A minus A will give me 0, the identity. Okay. So with this notation, let us now move forward. So let us see a particular example that I will give it for you to do. So let's say my set of the group that I want to declare is over the set of elements that belongs to Q, that is the set of rationals, such that this is not equal to -1, and I declare the operation between two elements as A added with B subtract A into B. So for all A, B belongs to G. So this is my operation. Now argue that is GO an abelian group. So now the way we solve it is as follows, that we solve it as follows, that let's say first of all, since A and B are rational, and these are addition, multiplication, subtraction operation, this will always produce a rational number. So therefore AOB must belong to Q. And since none of these are -1, so if none of these are -1, can you produce two numbers as -1? Just check it. Then I will say that closure property holds. For the associativity, you can easily see that AOBOC is basically A operated over B plus C minus BC, which is what? Which is A plus B plus C minus BC plus A into B plus, sorry, this is minus A into B plus C minus BC, which you compute will come as A plus B plus C minus AB minus BC minus CA plus ABC. And if you compute this also, doing AOB first followed by C, this will be the same as this. So the associativity holds. So this says that you also proven the associativity. Now the existence of identity element. So to have identity element, I need to prove AO identity is equal to A. So A plus identity minus A into identity is equal to A, which gives me identity is equal to 0, as I know I have given A not equal to -1. So this is my identity element of the set. So this is property 1, this is property 2, this is property 3, and finally I have the property inverse. So to have some inverse going, so I need to have A, let's say X is the inverse of A, is equal to 0, the identity, which means X is equal to A by A minus 1. This is perfectly a rational, this belongs to perfectly a rational number because A is not equal to -1. So this is my inverse of A belongs to G. Now the final one is about proving the abelian one. So just check what does AOB means. This is the final one, the abelian one. Is equal to A plus B minus AB, which is B plus A minus BA, the same thing, which is BOA. So this gives me abelian. So this is how we prove that something is an abelian group. Okay. So this is yes. So let me write the answer. This is yes. I hope you all have done along with me as well. So now with this definitions and some interesting properties of the groups, let us move to something called a subgroup object, the concept of subgroups. So as you can see, it's a subgroup. So therefore, we need to define here subsets of a particular group elements. So let G be a group. So this is given as our group. So we will define non-empty subsets H, which is a subset of G, and under the same operation, those elements which are present in this subset also forms a group. Then I call H. So in this case, if this happens, then I call H as a subgroup of G. Now, to give you an example, let us give an example. So you have seen that if I take the group as this number, this, let's say Z6 with plus. Now if I take 0 to 4 as my subgroup H, which is of the element, I take 0, I take 2 and I take 4. This set with the same plus. So this forms a subgroup of G because this is itself a group. 0 plus 2 will result 4, 2 plus 4 will result 0 under modulus 6 operation. So this will form a subgroup of G. So I will say that here in this example, H is not equal to empty and H is a subset of G as well as group. So H is a subgroup of G. The other examples you could think of is, so this is example 1. The other example you could think of is with the units. Just remember the units, I have defined that there are certain inverses of the unit. So let Z9 plus star in this ring, the units, if I consider the units of this ring, in this ring, the units of it, that is U9 with respect to multiplication, forms a group. Okay. So this is, let us consider this is my G, and I say H is those units which are, let's say 1, 4, 7 with multiplication. See that 4 has inverse 7, 7 has inverse 4. So all inverses are present. Identity is 1. So all this. So I can also take another set H dash as another subgroup rather. H dash as 1. 8 has inverse, it's 8. So I can take itself and form another subgroup. So all these are subgroups of, so all these are subgroups of U9 with star. So with this, let us try to see that what are the properties of subgroups that holds. So now let us go with the properties of subgroups. So property 1. So H, first of all, H is non-empty subset of G. Then H we call is a subgroup of G if and only if these two conditions occur. One, so let us say that G is under the operation O forms a group. This is our assumption. So one is that the operation O is closed under H, and secondly, so for all A, the second condition is that for all A in H, there exists, so the existence of A inverse also belongs to H. Let us try to prove this property. So there are two parts of the proof, since it is if and only if. So first, this side of the proof. It is very trivial because I know that H is a subgroup of the group G. So since H is a subgroup, H itself is a group. So H O itself is a group, and if all the things followed by definition, that this is closed and there should be an inverse if H is a group. The tricky part is proving this side of the proof, when these two are only given. So I have to prove the associativity and I have to prove the identity. To prove the associativity, first of all, so first let us try to prove the associativity. So to prove the associativity, we take three elements arbitrarily. A, B, C belongs to H. Now since H is also a subset of G, these elements also belongs to G as well. Since these elements belongs to G, so therefore in G you can say that this relation holds. So this also holds in H as well, because these are the elements from H. So if the operation holds and the operation is closed, because we assume that the operation is closed, so this also holds in H. So the associativity thing, we prove this proves the associativity of H under operation O. The second thing is the identity element, the existence of identity. So let us see that how the identity element can be done. So now see that for all A belongs to H, I have an A inverse belongs to H, and I know H is a subset of G. So for these two elements, so therefore this will give me A belongs to G and my A inverse also belongs to G. So therefore I can operate this due to the closure in G and can form E in G. So once I could operate it and can form H in G, therefore I can say that these operations are closed since my E has also must be inside G, because these two will form an element inside G as well. Hence, closure indicates E must also belongs to H. So this proves the identity of the group. So hence everything is proofs. Actually, here what we have done is that we have something which is called inherited the property of G. So here in both the cases we inherited, by since it's a subset, we inherited the property of G. The second properties of subgroup. So here is one property, we are going for the second one. This is very interesting since we have two conditions here. Now we can relax it. We say that G O is a group and H is non-empty, and we say that H is non-empty subgroup of G, and this is finite. So this is a new assumptions that we make, that is the finiteness assumption. Then H is a subgroup if and only if I need only one thing, this is closed in H. So this is pretty interesting because I have just want this one to have hold. Let's see how can we prove it. So this part is very trivial because this part is by definition. So it's a group. So by definition, I am not going into the details of it. By definition, the first property says the closure should hold. So by definition, this is true. This part, if only this holds and H is finite, remember that H is finite is my own condition. So what I will try to do is that I will try to form a set called H. So this is this set H is the set of all elements of the form AH such that H belongs to H. So since this happens, so now if A belongs to H, then you can see that obviously this set, for every H I have taken this element, since A belongs to H, then obviously this set must be a subset of H. So it implies that my AH length, the number of elements, the cardinality of H must be less than equal to H. But can it be less? If it is less, so now my claim is that if AH is less than the elements in H, then for two different H1 and H2, I will land up into this. But from here, in G, if you consider all these elements are in G, so left cancellation law will give you H1 equal to H2. Which will finally give you that here, from here, you can only get one condition, that is AH equal to H. Now the killing argument is that I have AH set which is subset of H, and I know that the number of elements are same with the assumption of H being finite. So this implies, this factor implies me that AH is nothing but same as H. Now when this is the case, now I have to find out whether the identity element and the inverse element exist. Now the existence of identity element is that we do find it in this way, that let us now go for the existence of identity element. So suppose there is an element B in H such that, see, I have done for every A belongs to H, I have done operated with a B and formulated that I will land up with some element in the H itself. So let us say that for an element A in H, I got that with some element B by operating with B. Now A, B, all are elements in G as well. So in G, I know that A, B, when I operate, then it also becomes AE because these are all part of G, which means B is my identity element and identity exists. For the inverse case, element case, since the identity exists, so identity is also a member of H. So just consider this is our very This is our very famous equation, H equal to H. So for an identity element that is present in H with A and some other elements from H will also be equal to that, because these two sets have same elements. So therefore for an A, I assume there is an element C which will produce in this set the element E. Now C to be the inverse, the side that is missing is that, can I prove CA is also equal to E? That side is missing. Okay. So to prove that one, what I will do is that I will do a CA square and try to think what it is. It is CA into CA. It means by associativity C, AC into A. AC is E, my assumption here. So C, E, A. So again, I can do it over EA and can make it as CA. Right? So what does this CA means? It's also part of G. So CA means CA into E. Now check this and this. It reveals that CA by the left cancellation law, CA is equal to E. So I have found out, therefore I have found out the inverse, because AC equal to E in H, which is equal to CA in H, which implies C is my inverse. Hence, I can say also that my inverse, yes, this holds. Hence, I can say that my inverse exists. Now, once I can prove all this, now we can also think about proving the associativity principle. It's pretty simple. So, everything tells that if this is closed and the finite thing makes it this as a subgroup. So, all of the examples that we have seen in subgroups groups are mostly abelian in nature. If you start from here, you see everything is abelian. One thing we have not discussed yet is any non-abelian group. It is a group, but it is non-abelian. We haven't discussed yet. So let us try to discuss a particular example which we call as non-abelian group. So does it exist or not? So by the way, just one thing to complete this discussion I forgot to mention is that since if you eliminate the finiteness, you will land up, for example, let us see one example. See that the set Z with respect to plus forms a group, and the subgroups of it are, so these are subgroups. You can form Z plus with respect to plus. But this is not a group, right? This is not a subgroup of this, because this is not a group, since for the positive integers with respect to plus, inverse doesn't exist. I do not have inverse. Similar thing happens for the natural numbers with respect to plus. So this is not a group. So why this happens? Because this happens due to the fact that I have eliminated this finiteness nature. So this happens. So therefore, by example, I can visualize that why that particular definition is very much required. You can visualize through examples. So let us now again go back. What we are trying to do here is that we are trying to make here the non-abelian group an example of it. Listen very carefully that what we are trying to do. Let us try to form a group this way, that we will try to understand the rigid motions of an equilateral triangle from a plane. So by rigid motions I mean that, just let me be very clear about the equilateral triangle a bit more. So let's say this is position 1, this is position 2 and this is position 3. Now I have points which are at same position initially. So therefore I I write this matrix pi 0 as where these points 1, 2, 3 lie. These points 1, 2, 3 lie. 1 lies in position 1, 2 goes in position 2, 3 goes in position 3. Now what I try to do here is that I try to give a 120-degree rotation left side. So my triangle will become this, where again this is position 1, this is position 2 and this is my position 3, but now my point has changed. Here it is 3, here it is 1 and here it is 2. So therefore now I can say that after this rotation, my new matrix is 1, 2, 3 positions will be in the place of 1 is at position 2, 2 is at position 3, 3 is at position 1. Again, if I try to give another rotation, let's say I try to give a rotation 120 degree left side. So this is again a rotation 120 degree. So when I try to give this rotation, my new triangle that I form, again this is my position 1, this is my position 2, 3. So you can easily figure out that this will be 2, this will be 3 and this will be 1. So therefore my pi 3 or rather pi 2, my pi 2 is the points 1, 2, 3 and their respective positions. 1 is at position 3, 2 is at position 1, 3 is at position 2. So therefore this is the rotational aspects that I given. So these are the metrics which denotes the rotational positions. There could be other thing as well, that I can also dictate what are called reflectional positions of this parameter. That suppose I have a triangle, so suppose I have this triangle in my hand where this is 1, this is 2, this is 3 and this is my center. What I will do, I will first try to reflect around this line once. So with respect to 2 and the center. So this will give me something called R2 with respect to point 2 being fixed. So now you see that your point 1 will reflect here, point 3 will reflect here, point 2 will remain the same. So therefore your point 1, 2, 3 position wise, if you write, it is 1 at position 3, 2 at position 2, 3 at position 1. Similarly, if you give another reflection, let's say this triangle. So this is your position 1, this is 2, this is 3, this is your center, and now you try to give reflection with respect to 1. So then what will happen is that your 3 point will be here reflected, 2 will be here, 1 will remain here. So therefore your reflection with respect to point 1 will be the 3 points, and then you try to write their positions as 1 will be at position 1, 2 will be at position 3, 3 will be at position 2. And then again if you try to reflect with respect to the last point that I have in my hand, that is point C, the point 3 with respect to center, this point. So therefore I have position 1, 2, 3 and I reflect it within this. So this comes 2, here comes 1 and 3 remains fixed. So therefore I get R2 or rather R3 is equal to the position 1, 2 and 3, and here I get the position as 1 has been shifted to 2, 2 has been shifted to 1, 3 remains same. Now what I claim is that I will try to form a group with the set of elements like this. My group will be with the set of elements pi 0, pi 1, pi 2, R1, R2, R3. And my operation is, so this, the second operations that you form, that I discussed, is called the reflection. So it is reflectional position. So these are motions that can happen to a triangle, equilateral triangle. So this is what we call, the operations are rigid motional positioning. So I just change the position. So here the first one are the points, the second is the position, every metric. So you can see that every possible number is present here in the position. So all possible rotations and reflections I have made of as a rigid motional positioning. So I get every possible permutations here. So I get these, the number of elements in G, or I would say the order of G, is basically 3 factorial here, which is 6. Now you see that this is a group. You will find this is a group because, let me give you a hint for that. This is definitely a group where you will find that your pi 0, which is identity in the positioning, this is your identity, and you will find your pi 1 inverse is pi 2, and so does pi 2 inverse is pi 1. And you can also find the R2 inverse, what is the R2 inverse, what is the R1 inverse, every inverse you can find it here. Okay, so I leave it to you to find R1 inverse, R2 inverse, R3 inverse. Now the interesting point here is that if you do pi 1 R2, let's say I do pi 1 with this operation R2. What does it mean? It means that I will do first positional change by pi 1 followed by R2. So it means 1 goes to 2, 2 goes to 2. So finally my matrix becomes for 1, 2, 3 positions. 1 goes to 2, 2 goes to 2, so 1 stays at 2. 2 goes to 3, 3 goes to 1, so 2 goes to 1. 3 goes to 1, 1 goes to 3, so 3 goes to 3. Now if you look at the other way, R2 pi 1, how does your metric will look like for 1, 2, 3? So first you do R2, which means that you do 1 to 3 and then 3 to 2, so 1 goes to 2. 2 to 2 and then 2 to 1, so 2 goes to 1. So here also I am getting the same answer. Sorry, here I missed it. 1 goes to 3 in R2, then 3 goes to 1 in pi 1. So therefore finally 1 goes to 1. 2 goes to 2 in R2, 2 goes to 3 in pi 1, so finally 2 goes to 3. 3 to 1, then 1 to 2, so 3 to 2. Now see, these two are not equal, which means that here what I found is this group is not abelian. But it is indeed a group because you have an identity, you have all possible inverses. If you find this, you have all possible inverses, associativity rules applied and all. So we call this group as symmetric group. So we call this group as symmetric group, and in particular we name it as S3 because it's the rotation of equilateral triangle 3. So for 4, that is with a square, all possible rotations and revolutions you can try out, and you can see there are 4 factorial, that is 24 such elements in the group will form a non-abelian group as well. So this is a particular kind of group, so people have renamed it using symmetric groups. Now to finish off today's lecture, we just will define one thing and then finish it off. So that thing is, as we have defined Cartesian product over sets, so over 2 groups we can define such kind of an operation. So we call it as cross operation. So this is a particular property or theorem. We can say that, let's say I have G, O and H star are two groups. Now when this is the case, then I can define a binary operations, like I can define a binary operation over G cross H set and define a binary operations like this. So this I defined as I define this as, let's say, if my G1, so for all G1, G2 belongs to G, and for all H1, H2 belongs to H, I define this operation as G1 operated with G2, this operation H1 operated with H2, this is the cross product that I want to mean, is, so this operation is basically, what do I mean by, rather let me go back a little, let me just go back a little and redefine this thing. So what we want to do is that we want to define this as G1 comma H1 belongs to G cross H with the operation we are doing with G2 comma H2. So we define this operation as G1 over G2 comma H1 star H2. So this is how we get for a tuple from G cross H we are doing. So finally what we receive here is that this is a over the direct product we formulate over this binary operation. So I leave it to you to verify why this is a group. So why this is a group? You just verify all possible combinations of associativity, identity element and everything. So this is the final definition which we could define over a cross product of two sets, a particular identity, associativity and inverse everything. So this comprises or completes the basic definitions of groups and subgroups and the operations over it. So in the next lecture we will also try to discuss more about the properties of groups and define certain special types of groups and their properties. Thank you.